A 240 volt DC shunt motor draws 15 amperes while supplying the rated load at a speed of 80 radian per second. The armature resistance is 0.5 ohm and the field winding resistance is 80 ohms. The external resistance to be added in armature circuit during plugging to limit the armature circuit to 125% of its rated value is. Okay. So this is a braking question, right? So what is the kind of motor? It is a DC shunt motor. So first we will draw the circuit diagram. Now what are all the information that it is given? It draws 15 amperes while supplying rated load at speed of 80 radian per second. So you can write down at rated load, the motor draws the load current. So this is the load current, this is armature current and this is the field current. So the load current is given as 50 amperes and the speed is given as 80 radian per second. Next, armature resistance is given as 0.5 ohm and the field winding is given as 80 ohm. Okay. So now what is happening? The motor is plugged. Okay. In plugging, what happens? The polarity of the back EMF is changed, so that effectively this behaves as a resistance which is connected across the armature resistance. The voltage across this will be the internal EMF that is generated plus the voltage that is given at the terminals. We can take it as supply voltage Vs. So now what is happening? During plugging, external resistance is added so that armature current is limited to 125%. So this is going to be IA dash, this is RA dash. IA dash is equal to 125% of its rated value, means 1.25 of this case. This is the rated condition, right? So the current drawn when it is supplying a rated load is the rated current. So IA dash during plugging is 1.25 times the rated current. So if this is the condition that needs to be satisfied, then what is the new armature resistance? That is the question. So first we will find out what is the armature current. Now the load current at rated load is given as 15 amperes. What about the field current? The field current will be Vs by Rf. Now Vs value is also given here, it is 240 volt, right? So you write down this as well. Vs is equal to 240 volt. So you can get If is equal to 240 by 80, which is equal to 3 amperes. From here we can get the armature current. What will be armature current? The load current minus field current for motor, right? So 15 minus 3 will be 12 amperes. So during plugging, the current should be 1.25 times 12. Now from here we will see how to get RA dash. From this circuit we have EB plus Vs is equal to IA dash into RA dash. So we just found out IA dash, Vs is anyways known, 240 volt, EB is not known. Now EB is dependent on the flux and speed, right? Now during the time that the plugging is starting, the speed will be same only, right? Same as the rated case. So that means, and the flux is also same. So that means the back EMF is same as the rated back EMF. Okay. So in rated condition, what is the back EMF? EB will be equal to Vs minus drop across armature. Okay. So this is 240 minus IA we got as 12 and RA is given as 0.5. So this is going to be 234 volt. So this, if you substitute here, you can get RA dash. RA dash is equal to 234 plus 240 divided by 1.25 into 12. If you calculate this, you're going to get 31.6 ohms. Okay. Now the question is, what is the external resistance value? So we have to subtract the armature resistance from this RA dash. Okay. So we are going to get RA plus R external is equal to RA dash, which means R external is 31.6 minus 0.5, which is 31.1 ohms. Okay. The next question we have, the armature resistance of a permanent magnet DC motor is 0.8 ohms. At no load, the motor draws 1.5 ampere from a supply voltage of 25 volt and runs at 1500 rpm. The efficiency of the motor while it is operating on load at 1400 rpm, drawing a current of 3.5 amperes from the same source will be. So we have here a permanent magnet DC motor. That means the field will be constant. There will be armature which will be connected to the supply, and there is going to be a permanent magnet. Okay, so we will represent like this. Okay, so next, what other information is given? The armature resistance is given as 0.8 ohm, and next we have the no load. At no load condition, the current that is drawn is same as the armature current here, right? So this is given as 1.5 amperes. And what about the supply voltage? This is given as 25 volts. Okay, and the speed in rpm, revolution per minute, this is given as 1500 rpm. So now we want to find out the efficiency of the motor in a different condition. Okay, so what is that different condition? This we can take as case 1 and this we will take as case 2. In case 2, what are the parameters that are given? The speed is given as 1400 rpm and the armature current is given as 3.5 amperes. So we will take IA1, VS1, N1, this is N2, IA2. Okay, so from the same source is given, so that means VS2 is equal to VS1, which is 25 volt. So now what do we want? We want to find out the efficiency of case 2, in the case 2. So in order to find efficiency, we will need input and output. Okay, but instead of either input or output, we can have losses as well. Okay, so from here you can see that the supply voltage and the current that is being drawn is given. So that will give you the input power. For a motor, electrical power is the input. And what is the electrical power that is being taken? Vs into Ia. So we have the input power, P input is equal to Vs2 into Ia2. So 25 into 3.5 will give you the input power. Okay, so now the mechanical output power we don't know. What we can find out is the losses. So that efficiency we can take as output, which can be found as input minus losses divided by input. Okay, if it's wanted in percentage, then we multiply by 100. Okay, so now the input is known, we will try to find out the losses. So the no load condition is given. From here we will try to find out the losses. Okay, so from case 1, what is the input that is being taken by the motor under no load condition? All of that will be used up in terms of losses only, right? Because there is no load, that means the output is 0. So whatever power it is taking, all of it is being utilized for losses. But what are all the losses that we have here? We have all the constant losses. So this will include the losses which are not dependent on the load. Okay, friction losses and the core losses, plus the armature copper loss. Remember, there is a resistance, armature resistance, and current is flowing through the armature resistance. So Ia1 square into Ra, this will be the armature loss. This will also be supplied by the input only, right? So this is what it is equal to Vs1 into Ia1. Okay, so from here you can find out constant losses, because the same constant losses will be there in this case 2 as well. So we want that constant losses. So this is equal to Vs1 is given as 25 into current is given as 1.5 minus Ia1 square is 1.5 square into 0.8. So this, if you calculate, you're going to get 35.7 watts. Okay. Now we can find out losses in case 2. This is going to be equal to the constant losses plus armature copper losses. This is armature copper loss, remember. So this is what? Ia2 square into Ra. Okay. So we know the constant losses 35.7 plus IA2 square RA is 3.5 square into 0.8. So we can get the efficiency is equal to input minus losses. So 25 into 3.5 minus 35.7 plus 3.5 square into 0.8 divided by the input power, just 25 into 3.5. Okay. So this, if you calculate, you're going to get 48%. A DC shunt generator delivers at 45 amperes at a terminal voltage of 220 volt. The armature and the shunt field resistance are 0.01 ohm and 44 ohm respectively. The stray losses are 375 watts. The percentage efficiency of the DC generator is. So this is also an efficiency question. This is a generator, a shunt generator. So what will be the current directions? This will be IA, this will be the load current, and this will be the field current. Now what are all the information that is given? It delivers 45 amperes at a terminal voltage of 220. So since it is given as delivering, we will take it as the load current. So IL is 45 amperes and the terminal voltage, if you take as VT, then VT is equal to 220 volt. Next, armature resistance is given as 0.01 ohms and the field resistance is 44 ohms. And the stray losses is given as 375 watt. Now what is the efficiency? Okay. So what information do we have here? It is a generator and the electrical output that it is giving, VT into IL. This is known. Okay. So we know the output power. So we want the losses so that we can find the input. Now losses will be, copper losses will be for the field winding as well as the armature winding, and also the constant losses. Okay. So the constant losses we can take as 375 watt. So you can first write down P output is equal to VT into IL. This is 220 into 45. Then losses, the copper losses is given by IA square into RA plus IF square into RF. RA and RF we know, IA and IF we have to find out. So what is IF here? IF is easier to find out, terminal voltage divided by RF. So this is going to be 220 divided by 44. This will come out to be 5 amperes. And from here you can find out the armature current. This is going to be IF plus IL. So 45 plus 5 is 50 amperes. Okay. So from here copper losses, you can substitute both of them here. 50 square into 0.01 plus 5 square into 44. You're going to get 1125 watts. Okay. So now you can find out the efficiency is equal to 220 into 45 divided by output plus losses. Copper losses is 1125 and the constant losses is 375. Okay. So this, if you calculate, you're going to get around 86.8%.